Welcome to Energy Talks, a regular podcast series with expert discussions on topics related to power system testing, data management, and cybersecurity in the power industry. My name is Scott Williams from the podcast team at Omicron, and I will be your host. Hello, everyone. In this episode, we discuss the challenges protection engineers face over time due to the transformation of energy systems, advancements in protection technology, evolving maintenance requirements, and keeping up with the latest developments to do their work effectively. Two seasoned experts in protection testing join me to describe these challenges in depth and offer their experience and expertise to suggest ways to address them. Both of my guests presented this topic at a recent Omicron German user meeting focused on protection and control technology. My first guest is Ignaz Hüber. He studied electrical engineering at the Technical University of Graz in Austria. From 1987, he worked at Kellogg-Cantner Electricity as a protection technician in operations. Until his retirement in 2018, he worked in management positions at K&G Canton Network. Until 2016, he was the Protection Technology Department Chairman at Austria Energy. He has been with CIRED in the Technical Committee Session 3 since 2009, and since 2021, he has been Chairman of CIRED in the Technical Committee Session 4, Protection, Control, and Automation. Hello, Ignaz. Welcome to Energy Talks.
Thank you. It's great to be here.
Also joining me is Oliver Skrbinjek. Oliver has been working with protection technology in medium and high voltage networks and with the entire process of automation technology within energy distribution since the mid-1990s. He heads the secondary technology department at Energy Netz in Steiermark, Austria. In addition to standardization and communication in energy distribution systems, his current focus is on protection technology, cross-system principles, expert questions, and information security in technical systems. Oliver, I also extend a warm welcome to you.
Thank you, Scott, for the invitation, and I appreciate to be here.
Thank you both for joining me for this episode about the challenges in the life cycle of a protection engineer. Could you please describe the challenges caused by the technological transformation of protection technology?
Yes, I will answer this question. First, I want to explain that when I started as a protection engineer in 1986, there were no digital relay. Everything was mechanical, and there are black boxes, and the mechanical relays had all one function in one relay. The big challenge was coming with the digital relays. And this was the first time all the functions were in the software and there was no mechanical equipment inside. And I think this was the first big challenge I had in 1986.
Very good. So what are the challenges in protection technology due to the transformation of energy systems?
I think, as you know, there are several changes which are caused by the energy transition. First of all, I would like to mention out the decentralization of generation in kind of a lot of inverter-based infeeds, which caused at the end a change in the load flow. A second point I would like to mention out are the associated retrofit and expansion measures, which results for the protection engineer in an ever smaller impedance. And last but not least, I would like to point out the problem of the reliability of the fault detection with regard to low short-circuit currents. I think an upcoming challenge could be also the necessity of sector coupling. Here you have to expand the focus to the protection area from the well-known alternating domain with an overlap to the, for example, GC domain, as well as to other domains like heat, gas, traffic, and so on.
So what are the drivers of these current challenges, and in which domains can they be found?
I think the drivers are not coming from standards and directives. This all comes later. First, you have a development and you have devices, and then this is the next step, I think. The driver, it was the development of the first microprocessors, I think, because it was possible to realize protection functions in the software, and this was the first time it was possible. So it was really very different technology. And I think the driver is coming because you had the possibility to manufacture very small relays. You don't need so much space, and you can include not only one function in a relay, you can include several functions in one hardware. So I think this was the big challenge and the drivers.
So in terms of consequences of changing network operating conditions, when does the increasing penetration of inverters cause problems?
I think the increasing penetration of inverters should be a general problem for operators if, for example, increasingly more islanding networks are created. That could be happened easily in case of fault isolation in a compensated network. There is also a completely other problem, namely the change of the starpoint treatment towards a starpoint isolated network operation in an isolated grid. In my opinion, current legal requirements, such as the European Grid Code, favor such islanding significantly. An example which can be pointed out is the increasing implementation for grid forming converter instead of the well-known grid falling inverter. But generally, from the point of a protection technician, I would say as long as the grid has a connection to the main, to the superior grid, there is at least nowadays still no big challenge. In summary, I can say that losing the main can cause a problem as well for protection technicians as for the system operator.
Do existing protection concepts still work as the network expands?
It depends, I would say. But in principle, the protection concepts also work for network expansions. However, a suitable check is necessary in any case.
Do protection concepts at higher voltage levels have to be transformed to lower levels?
Oh, I think that's an interesting question where I have to go maybe a little bit more into detail. Just before we talked about problems which can be caused by predominantly inverter-based in-feed. And in case of a fault, one consequence is the weak in the short circuit current. Depending on the fault location, the expansion of the voltage funnel can also be a big problem because finally the clarification time is relevant because this gives the total amount of loss in in-feed. Because if the voltage funnel is very big, you also lost a lot of in-feed by under voltage protection system. So to reduce the risk of this imbalance in power, today network planning departments of European transport system operators do investigation to special fault cases to figure out necessary to-dos to ensure the stability in our transmission distribution system. One necessary measure to do could be the reduction of the fault clarification time. To be inside the fault through characteristic from the network code requirements for generation. This measure can reduce the loss of in-feed in case of fault significantly. Another use case could be the necessary change of the fault detection concept in medium voltage grids towards under-impedance or voltage-controlled overcurrent trigger. But there are also new untypical protection schemes in that and also still in use in different distribution system networks, like the protection against increasing of current in time.
So in terms of current and future technological development, who determines what is developed today?
Scott, I think that's a good and interesting question. And in the past, the answer could be very simple because the lead of developing was on the manufacturer side and also on the side of the bigger transmission and distribution system operator. Nowadays, the decision what is needed is defined by many different causes and sources. Here we have, in my opinion, to distinguish between software development and in kind of updates and upgrades and hardware developments according to the requirements of different domains. In general, we have distinguished between protection functionality and all the other functionality which is driven by many other domains like the information technology, the security, network operating, and so on. From the side of the protection functionality, the physics behind is still the same. Here we have to act according to the requirements and the changes in the grid, especially at the protection object and the framework condition. There, the dominant of development must be done together from the manufacturer and the grid operator. This is not an easy task because there are many operators with different requirements and the manufacturer has to try to meet all requirements and still remain standardized and maintainable. The last point I want to mention out here is the fact that the different domains which have to be considered in the protection system have different lifetime cycles. A simple protection function as a part of a digital protection device has a life cycle of around about 15 to 20 years. The life cycle of network equipment, which is also part of a protection device, is with around about 5 to 10 years significantly shorter. Finally, security features, which increasingly require more system resources, have in the most cases the shortest lifetime cycle. In many cases, security features often cannot longer run on hardware older than 5 years because of the resource and performance reason. So we can see that different life cycles are also another driver for triggering new developments.
So what is really needed and which needs are artificial?
I think people sometimes forget that the main task of protection is still the protective function. And when I follow the discussions on conferences, therefore I can say what you always need is the protection function. And the question is, do you really need so much additional functions and data and all the services around the protection? Is this really a need? From my experience, I can say that many things are not necessary. It is an artificial need and nice to have, but sometimes hardly used.
So how must the organization adapt to the changed technical framework?
As you already heard, digital protection relays offer a lot of functionality, where the protection engineer not always can act independent. Especially the communication, the network and the security settings, as well as the associated functionality, must be defined in cooperation with the therefore responsible department. Further, with a little sustainable thinking, we not only have to see the digital protection device, we have to look to the whole digital substation and all components that are responsible for the functioning secondary system, as well as the processes and interfaces behind them. If we do this, we will find in several cases optimization potential, such as reducing interfaces between departments by little adaptation in organization. However, this only can make sense if you carry out in advance a carefully analyze of all regarding processes and the skills and competences of each individual department. Taking into account the facts mentioned before, it could make sense to adapt an organization, for example, including the responsible as well as the knowledge for the cybersecurity in the technical environment into the department for the grid operation, or merging the responsibility for telecontrol system, automation and protection, as well as the responsibility for decentralized network design and technologies into the same department. Best case could be if this is also the department with responsibility for grid operation. But this is only a little bit food for thought, because every transmission distribution system operator has to develop his own strategy, which fits with his other processes and corporate philosophy.
Very good. Thank you, Oliver. So what are the consequences of rapid development cycles?
I think some developments improve the protective functions. This is important. But these are not rapid developments. I think you must be careful changing some basic functions. A very rapid developments in the environment of the protection function. This makes everything more and more complex. This is a big problem. You have to look at both terms of protection and operation. The consequences of the rapid development cycles are that the user must constantly learn and often cannot longer follow the cycles. This is my experience, and there are rapid changes, especially in communication in substations. And this can be a big problem because the protection engineer is not maybe the professional in the communication part.
Thank you, Ignaz. So how can targeted development of protection systems with the involvement of users be ensured?
In my opinion, the most important thing and also a success factor is the communication between the manufacturer and the user. Because how should the manufacturer know what the user needs? I think it's very important that they have to meet each other, for example, at conferences or user meeting. This exchange should be not unidirectional, because also given restriction by laws, for example, and rules, have to communicate to the customer, because that helps him to understand about the clearly restricted behavior of the manufacturer. In some countries, there is also an association for energy supplier, mostly with a group for protection engineer, where they can discuss the problems and do an advanced exchange of experience. These country special groups could also be a good address for an exchange of information from manufacturers regarding functionality, but also detected malfunctional from user side. So summarized, can be said that during the whole life cycle of a technical equipment in the critical infrastructure of a grid operator, a close cooperation between the manufacturer and the user have to take place. This starts at the product developing, is going on with common pre-qualification and exception test, and runs via the operation life cycle, which represents the longest process until the end of the support. It may sound strange, but buying a device also means entering into a lifelong relationship with the manufacturer.
Ignaz, could you please describe the aspects of innovation versus robustness in the development cycle?
Yes, I know this is a difficult question. The question is, when is a system really robust and stable? I can say that resilient innovation should have a minimal risk in operation, because this is very important. You must always have a look in the practical side. The acceptance and trust comes with operational experience, I think. You cannot say this when you are developing a new function or you think you are doing something better. You really know this when you have experience in the operation. You should always have experience in this protection. You should always have a plan B if something is going wrong.
Very good. Thank you. Oliver, when do innovations make sense?
Well, I think innovation in general makes sense because innovation moves us as user forward. But I think an innovation has to be critically analyzed and rated. You have to ask yourself the question if each innovation is necessary and if this special innovation brings the benefit. Sometimes it's necessary to test an innovation to learn and to recognize a possible benefit before using it by yourself. Especially big innovations must be evaluated by different experts of different domains. Decide commonly the benefit. Sometimes it also makes sense to include not the whole innovation, but only some extracted parts which bring the additional benefit to existing system and implementations. So I will say it depends on the use case if it makes sense or not.
Very good. What are the important elements of a resilient innovation?
The important elements in innovation are the strategic direction, the cultural change, the risk management, planning, scenarios, and so on. But I think all these points are very important for resilient innovations. But we must not forget the user. I think you must always have a look at them. The user must understand and accept the innovations. Otherwise, it will be difficult. And this can only happen in good cooperation with the manufacturer. And I think it's important to have working groups. Together you have exchange of experience. I think this is also very important.
Very good, Ignaz. Thank you. So when is a system robust?
I think the definition of robustness and stability is regarding the protection function quite easy. You can imagine if the system tripped correctly in time at the fault and otherwise the system has no functionality in the meantime, we could talk more or less of stability in the robust system. Expanding the system, for example, with communication to the protection system with signal compensation, the part of communication as well as the second protection device must be taken also into consideration if you do a rating regarding to the stability and the robustness of the system. In relation to software, meaning updates and upgrades, we can speak about robustness and stability if after an update, known bugs have been eliminated and no new bugs have been added. Experiences of the past had shown that the quality of software update is not always as good as expected. They could bring also more new bugs and malfunctionality than cleaning up old bugs. So in this relationship, we can talk about robustness and stability if the quality of updates and upgrades is very high. If the user is not longer a beta tester for the manufacturer and updates do not released every 2 weeks. I think that could be a definition.
Very good. Thank you, Oliver. So now we've come to another major topic area, and that's the maintenance process requirements of evolving protection systems. How are maintenance process requirements evolving with new technology and changing network environments?
This is a difficult question, I think, and I try to find a short answer for this. The first step is to assess the effort involved, both in terms of personnel and money. Mm-hmm. I think also safety regulations and standards should be complied with. And the responsibility is also a question. And I think the responsibility lies with the utility company at first. But a large part of the responsibility lies with the protection engineer.
Very good. We're getting into those challenges that process engineers face and what they need to think about. Can you give an example of a risk-based so-called patch management process? How does it work and what are the steps involved?
I think you could handle such a patch process within 3 steps. The first step, I would say, it's the collecting step. It's very important to collect all available known vulnerabilities. For this, it's recommended to make a contract with all the manufacturers who are in use in your system to get all the vulnerabilities and the reports in time. In the second step, you have to evaluate all the collected vulnerabilities for each domain and make an assessment of weakness regarding the usage in the individual system. This represents more or less the risk analysis you have to do as operator of a critical infrastructure. And as a third point, you have to start the rollout. Here, the individual domains have to evaluate all the possible solutions regarding to their effectiveness. After choosing the best solution methodology, unwanted interactions between the measures have to be checked. Finally, the actual rollout takes place. Summarize, you can say, you have to collect vulnerabilities as a first step. Then, as a second step, you have to analyze the impact as well as the associated risk and make a decision regarding to the requirements of measures. Finally, a third step, if there is a necessary to measures, all domains have to evaluate their individual measures before the real rollout of the measures can take place. It do not only sound complex, it's a real complex interdisciplinary process which have to be well organized and implemented in the daily business of a company.
Very good. Thank you, Oliver. Now we're coming to a final point here, and that's given all of these challenge points and technology, changing network environments, and also maintenance requirements, how does this transform the protection technician role and also what the protection engineer needs to know? How has the know-how of protection technicians evolved with changing network environments, technology, and maintenance requirements?
Yes, I think this is an important question, and I can answer that. Expertise, so-called know-how, is acquired through learning and experience, and this you cannot do in a short way. You need time for this, and from my point of view, it needs years to have a know-how, yes, to build up know-how. In large companies, I think it's easier to have expertise in one part because you can divide this to different topics and you have more than one engineer there, so it's easier. But it's a big problem there when you have a small company. And if you have only one protection engineer, it's really difficult to have this know-how in different parts of protection. Experience shows that this is not possible in small companies, I think, and this is the need to have working groups to exchange the know-how between the colleagues.
What will the future responsibilities of protection technicians look like in a secondary system?
Well, I think the main responsibility is the same as it was in the past. A protection technician will still be responsible for the whole protection system, as well as the definition of the requirements for the needed additional services, like the maximum of round-trip time, for example, or delays in communication functionalities. But protection devices are also part of the secondary system, and they have to act with this system regarding to the rules and requirements, which are defined by other responsible departments. For example, the department who is responsible for the local communication network in the substation, or the department who is responsible for the information technology. In this case, the protection technician is responsible to fulfill the requirements of the other stakeholders. The protection technician can support these requirements by, for example, the correct settings of the VLAN taggings by supporting SIEM system with syslog event or SNMP response, for example. Finally, I would like to mention that in my opinion, every protection engineer is also responsible to be up to date in the field of protection, but also to be interested in all fields of possible points of touch to the protection device and to new developments.
Very good. Thank you, Oliver. Ignaz, how will the future workload require purchasing expert services?
Yes, as I told you before, it's difficult in a small company to have all this knowledge and know-how in one person. So I think in small companies, especially, it's a need to get experts from extern. So you have to be brought in this expertise. I think you must do this also in bigger companies because you cannot know everything. And experts will have to be brought in a company, in a bigger company also. I think it's a need in the future because you cannot know everything and every development you cannot follow.
Very good. So my last question to wrap up is, how can technicians ensure proper training and keep up with the changes to network operating conditions, technology, and maintenance requirements?
Oh, I think my simple but I hope very effective advice is be active and be a member of the protection community to discuss with colleagues about protection. Use as often as possible the opportunity of attend events for protection secondary technology, as well as user meeting like the one of Omicron. Build your own network with colleagues and experts. You will see this improve your knowledge and it can help you a lot. After reaching a well level of education and experience over the time, you will see that you are not longer more an asking member, but a member who passes on his acquired knowledge to other younger colleagues. By this way, we can ensure that our community lives. A second important thing is to be open for new challenges. Do not be shy asking colleagues and experts from other domains. You only can learn and be better if you are asking. Try to think outside the box, beyond your field of experience, and you will recognize new connections that will make your everyday lives much easier. With time, you will reach a much better understanding for the whole system, and you will be able to communicate with colleagues from other domains, maybe not in the expert level of their domain, but on a very high level. I think that can help you and bring you forward.
Very good. Ignaz and Oliver, thank you for joining me for this episode of Energy Talks and sharing your insights into the challenges of a protection engineer's life cycle.
It was a pleasure for me to speak from the wealth of experience in the life cycle of a protection engineer. I would like to thank you.
And Scott, also from my side, thank you. And it was also a pleasure for me to be here. Thank you.
And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Omicron has several years of experience in power system testing, data management, and cybersecurity in the power industry, and offers you the matching solution for your application. For more information, be sure to visit our website at omicronenergy.com. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.